All right, so we're finishing up imitation learning, and this was really just part of the class. This is a very practical thing to know about. If you run into situations where imitation learning will be a viable approach for you in a number of cases. And just to remind you, so the most basic imitation learning approach is simply you have some way of generating trajectories from a good policy or some policy, and you turn those into supervised training examples, where each example is, well, here's a situation, like this is an Atari situation, and here's the action that the expert did. Right? So we call this an expert policy. Then you can just use a supervised learning algorithm to try to predict the action of the expert from the inputs. Right? So easy as that. Now, let's test to see what you learned from last time. So what is one of the fundamental problems that can arise when you do imitation learning in this way? So I watch him do something, and I just learn to memorize it by watching him. What can go wrong with me if I'm then going to execute my policy, and why? Should we go through the whole lecture again? Anybody? Yes.
If you deviate from what you saw, then you'll start making like progressively worse decisions than you saw them do.
Right. So one of these early examples. This is actually a very early example of where this issue arose. Sometimes these obvious issues don't come to mind until you see them. Is when in the early 90s they were trying to train cars to drive via neural networks by mimicking humans. And the car would slowly veer off the road, right? And even though no human actually slowly veered off the road, and what was happening is you learned the policy from the human, you had a little bit of error in the steering wheel directions, and it would go a little bit off the road, and then you start getting into situations that are a little bit different than the data you were trained on. And you make slightly more errors, and then you get into even worse situations that are different from what you were trained on, and you make more errors. And so that was the notion of error propagation, where we said this is what you were trained on, then you learn a policy from that. Here it's good, it executes the first action well. The policy makes an error here and starts deviating. And now this is data that you've never seen before, perhaps, and you're just completely confused. So that's what can go wrong, and that's why theoretically this form of imitation learning can be this much worse. So if I've learned to accurately model what I see him do with epsilon error, epsilon can be small, my policy when I execute it still might be this much worse than his policy in terms of value when we actually execute them. And if epsilon's tiny, that's great, but h squared can be really large. H is the horizon, and so epsilon has to be incredibly small to make up for that, right? So this won't always bite you. It won't always be an issue, but it can be, and I've seen it be an issue. And I've seen it not be an issue. So it's sort of an empirical thing about whether you're in a domain where this is a problem or not. So we talked about how you can overcome this, and the ways of overcoming it are generally it's kind of obvious. You execute the policy that's learned, and then you do some more learning along the policy as it's executing, right? So we see, the car is starting to veer off the road. We'll just tell the car what to do in those situations. Just turn the wheel a little bit to the right because you're veering to the left. And then the system will basically collect more data. You collect more data this way, and eventually you're hoping if you keep on doing this, the data distribution that you learn on will be similar to the data distribution that the policy actually generates. And that's sort of the fixed point of this situation. And there's theory in these papers, different forms of the theory, that basically says for some domains that we'll just say they're characterized as being recoverable. So we're a driving domain is kind of a recoverable domain. In most situations, if you veer off a little bit, you can recover. In those domains, you can get rid of this h squared and turn it into h. some domains where you can fall off a cliff with any minor deviation, you'll always have to have the h squared, theoretically. All right, so any questions about that? All right. So the other thing that we did is we talked about, well, where the heck do you get these expert trajectories? Well, one is you can get it from humans, right? So this would be a situation where you want to automate a task that is done well by a human, but the human finds it boring, for example. And so this is, you just collect data from humans, and that's what they did to bootstrap AlphaGo. So they use 30 million Go positions, and we'll talk about this a little bit later in the class, of expert players to basically learn an initial policy from that data. And they didn't do any of this fancy sort of dagger style retraining. They just learned a deep network on the data. And that gave them a good starting point for reinforcement learning. Right? That's basically what they did. So they bootstrapped reinforcement learning with imitation learning, and that's something you'll find countless papers on. It's a pretty common thing to do. You'll see, if you're paying attention to DeepMind, what they're doing now, they're now looking at StarCraft. So Alpha Star is the system that they're playing with, and I would guess within a year, probably less, they'll be beating the world champion in StarCraft. Well, the top players in StarCraft. They've already beat some pretty good players. It's just a matter of time now. And a huge part of getting that to work was bootstrapping with imitation learning. Like there was no way you could just start from scratch with reinforcement learning. And if you know about AlphaZero, we'll talk about it later. StarCraft, you're not going to be able to do the trick for bootstrapping that they did with AlphaZero. So we'll talk about that later. But imitation learning was essential there. And it's pretty interesting, though, because they were learning from lots and lots of trajectories and games from different skill levels and different players. So it's still kind of amazing that got them anywhere. But they still had to do reinforcement learning after that to improve. All right, so that's one thing. Any questions about that?
Did they decorrelate the positions in the trajectory for Go?
Say that again?
Did they decorrelate the positions?
No. So you just have, I don't know how many games they had, but at the end of the day, they just had 30,000 positions. And I'm sure they did some sort of mini batch updating, so randomly sampling, and yeah. So you probably, it probably would have been a bad, well, yeah, who knows? You probably it would be worse to just sequentially go through all the games and update, similar to how DQN likes to decorrelate. That's just a general rule of thumb. Decorrelating data for supervised learning is usually a good idea. So that's that approach. The second approach, which can be very relevant, and this is something you're seeing more and more of in robotics, for example, but other areas as well. Anywhere where you have a problem that you have a slow solver, maybe it's slow, but it's slower than you want. So in robotics, for example, maybe you want to be able to grasp objects, and if you have a planner, we'll say, like a trajectory planner, that if you give it enough time, it will find a really nice way to grasp an object, right, by planning through the trajectory space. But it takes a long time, and you don't want your robot to sit there for an hour and think about how to pick up a cup. So what you can do is you can use those slow planners as experts that you can then learn a fast approximation of the planner. You can learn to imitate the slow planner. And so you want to learn a fast approximation to a slow controller, we'll say. And this can be done in games as well. So if you have you want to play chess really well, you'll take a fair amount of time deciding what to do. You'll use tree search to decide what to do. If you want to get something that can play speed chess, then you could try to train a neural network or whatever you want on the actions as selected by the slow planner. Okay, and so sometimes you may have heard, who's ever heard of system 1 and system 2, like in the brain? People talk about these things, right? Yeah, so I can never remember which one is system 1 and system 2, but there's a book, Acting Fast and Slow. So let's just say system 1 is the deliberative part of the brain, where you think and you reason, and system 2 is sort of the reactive part, right? You can do a lot of things without thinking, right? A lot of times, and what often happens is a new skill will start out as system 1. You have to think about it. You have to think about what you're doing, and it becomes a system 2 routine after you've done it enough. Like you've played chess a lot, and eventually moves become obvious to you. It doesn't feel like you're deliberating about them anymore. Some moves you do have to deliberate, but a lot of things that were not obvious originally become obvious, and they're just immediate. And that's sort of an analogy here. You're going to learn from a slow system 1 system to make it really fast, and that fast thing is like a system 2. Yeah, hopefully I didn't get those mixed up, but it doesn't matter. I think they should just call it fast system and slow system. It would be a lot easier to remember. So here's an example of that. Lots of examples in robotics nowadays of this. So this is a fairly old example now, but it was pretty interesting at the time. So we've done a lot of work like this in our lab as well. But so this is Atari, and this is DQN. So we learned about DQN and how it learns to play Atari games, right? And this is showing the performance on a few games. Now, we're going to learn about what's called Monte Carlo tree search in the next part of the class. This is basically you can build a tree and you can use it to play Atari games. So at every step of the Atari game, this is incredibly slow. You can stop the game and you can build this tree that looks ahead at the future trajectories of the Atari game under different action sequences. And you can use that tree to decide what to do right now. Right? So you're thinking ahead. I don't know how many moves. Maybe you're thinking ahead, 5 or 6 actions ahead, and that's a very slow process. But you can simulate playing an Atari game that way, and it's just going to take you 3 hours to play one game of Pong, for example. But the actions that you select are going to be quite a bit better, at least at that time, than the best reinforcement learned policy. And this is what you see here. So, I don't know what happened there. So Monte Carlo planning, this is that very slow routine, does quite a bit better than DQN, the reinforcement learned policy, on most of these games, right? So you've got 7,000 here versus 4,000, 2,000 here versus 500. And today probably the best RL method is better than these, but we're trying to make a particular point here. Now, yes.
Do the red numbers indicate maximum score?
I don't remember what these numbers are. I'm guessing. I think they were fair, reasonable numbers, but I don't remember. You'd have to look at the paper. What I'm covering in red here is just the max across these columns. Yeah. So it's just the best of these. So now you could say, well, we've got this really slow thing that's playing Atari. It's taking 3 hours to play a single game of Atari. Well, why don't we just collect that data, play a bunch of games, and then use it to learn a policy via imitation learning and supervised learning. And in this paper, they do sort of the naive imitation learning approach, and they also do Dagger. I forget which these numbers are from, but you can see they learn a policy it's not quite as good as the original planning algorithm, but it's often better than what DQN was able to learn via reinforcement learning. Um, so yeah, and generally, I guess it's always better than what DQN was able to learn. So that's a nice illustration of how you can use imitation learning to do a little better than reinforcement learning in some cases. And of course, you could take this policy and you could use it as a starting point for reinforcement learning and try to improve from there. And that's what they did with AlphaGo, and that's what they're doing with AlphaStar. Um, yeah, and you notice usually they do a little worse than the planner, but some cases it's just lucky, and who knows why it does a little better. There's no particular reason that should happen. Um, so yeah, any questions about this? Yes.
For the Monte Carlo planning, the re-expansion scheme or policy that they must be using, won't it suffer from the same problems that Monte Carlo online learning suffers from, in that it does not fit a MDP inherently, it's just using the final rewards from the rollout and using them. So would it be better to use some kind of a TD update there instead of a Monte Carlo rollout?
Yeah. So your point is that so whatever you're using for your look ahead search, those approaches do suffer from a lot of the same issues that reinforcement learning suffers from. So if you're building a search tree and you don't get any reward until depth 100, a search can do horribly as well. And so basically the way I like to look at this is it's almost like you're just so it suffers from the same problems, but you're basically putting in a lot more work at every state. So it's almost like you're trying to solve. We'll see this when we get to the tree search, but it's almost like at every state you're running a reinforcement learning process just starting at that state every time. So every trajectory starts at that state, and you spend a lot of time doing that, and eventually you find a reward that's good for that state, an action that's good for that state. But you can certainly set up problems where these tree searches will give you no useful information. Just happens that these are not examples of that particular case. They suffer from sparse reward, which is something that a lot of people don't actually recognize. You think Monte Carlo tree search is sort of a magic thing that can solve any problem, but fundamentally it's very similar to reinforcement learning and has the same issues. Yeah, so I look at this approach as reinforcement learning for these hard problems. It spends so it collects data very cheaply, right? The data it collects is very cheap, but it's very noisy, right? So it just runs trajectories and it tries to estimate gradients, but they're very noisy gradients. It doesn't spend a lot of time trying to figure out how to make the, let's say, supervision or target values for that data more accurate. This imitation learning approach is sort of the opposite effect. It's spending a lot of time at each state you encounter to try to get a more accurate estimate. You'll get less data that way in the same amount of time compared to a reinforcement learning agent, but it will be more accurate data. And so it's sort of a trade-off there. Like lots and lots of very inaccurate data and you do lots more updating, or less more accurate data. And I think eventually the less more accurate data is going to be something that wins out, especially when you have more powerful planners, like specialized planners for trajectory planning, for example, in robotics, because those planners are really developed for the application, and they can really exploit the problem domain. All right, so any other questions about this? Yeah, very useful thing to know. You can kind of do this in any domain where any problem where you have a good but slow solver. All right, so that is it for imitation learning. Now we're going to make sure. Okay, I am recording. Now we're going to change gears and move to the next part of the course, the next topic. And this is the topic that we'll kind of end on. There's multiple slide decks for this, but we're gonna study Monte Carlo planning now, and this first part is going to focus on something called bandit algorithms. But we're first going to describe the general formulation of Monte Carlo planning, and then we'll talk about the bandits, and then we'll move on, and eventually we'll get to Monte Carlo tree search, which you just saw an example of a moment ago. So, the real challenge is to solve really large MDPs. And what have we considered so far? Well, we've considered model-based planning. It assumes the MDP model is available. And what we've learned so far, value iteration, policy iteration, those methods kind of only are going to work for relatively small, manageable state spaces, right? So you're either going to have to take the problem and somehow abstract it and compress it into a small state space, or you're not going to be able to apply those methods. So we're going to consider ways of overcoming that. But the other way that I mentioned, which we're not going to get to in this class, but it's worth knowing about, is just, as I've mentioned before, there are methods that try to take a description of the MDP, a compact description, and have algorithms that reason about the compact description to come up with a compact policy. So this would be like giving the system the rules of a game, like in maybe not textual form, but a formal language, and the rules of the game are going to be much shorter than the MDP itself. All right, there are many states in the game, but the rules can be described compactly. And then you have a system that reasons about those rules and comes up with, we'll say, a symbolic representation of the policy that's much smaller than the size of the state space. These are interesting ideas, but we're not going to talk about them. We don't have time to talk about them here. But scalability is still an issue there. The other approach, the one that we've been talking about, is to use reinforcement learning. This is maybe one of the more popular approaches these days, where you use reinforcement learning with function approximation to solve a really hard problem. And that will work in a lot of cases, but it does have limitations, and we've pointed to a lot of limitations that reinforcement learning has. There are some problems that it can't even get off the ground, right? If you have really sparse rewards, in some cases you're just going to flail around forever and never learn a good policy. And so then there's a whole art to how to bootstrap the RL. We saw imitation learning. There's other approaches such as shaping rewards and whatnot. But another weakness of reinforcement learning is the basic algorithms don't fully exploit the types of simulators that we often have available to us. Right? A lot of the reinforcement learning algorithms are sort of formulated in this, really, it's almost they're formulated from the standpoint of an animal learning in the environment, in the real world, or a robot learning in the real world. But we rarely ever run reinforcement learning algorithms in that setup, right? Because they're just way too slow. They require millions of trajectories. And so you're going to be running reinforcement learning usually in simulation. And when we have a simulator, it's often the case that the simulator will allow you to go anywhere you want in the world and take any action you want. But the reinforcement learning algorithms don't exploit that necessarily. They just kind of pretend that, I'm stuck in this world trajectory and I can't, teleport to different places. So the reinforcement learning algorithms, as we've formulated them so far, don't really exploit the capabilities of the simulators that we might have. And we'll talk about that in a little bit. So that sort of brings up the idea of what we're going to call Monte Carlo planning, and I don't know how common this term is, but it's the term I like to use for this class of approaches that are going to try to exploit the availability of a simulator to make good decisions in an MDP. And a lot of times we have good simulators, right? Or we can learn a good simulator from data. And these are just two examples. So Klondike Solitaire, if you want to learn a policy, or you want to get a policy that plays good solitaire, well, we've got a simulator for solitaire. That's easy enough to cook up. Might as well use it. This is another domain that we've worked on in the past, fire and emergency response. A company in town has a simulator for this, and it's driven by data that historical data of 911 calls. So you can simulate things pretty accurately. And so why not try to exploit the power of the simulator for making decisions? So the picture that you should have in mind here is we've got our typical agent that we want to act in the world, and the agent is giving actions to the real world and getting states and rewards back. And reinforcement learning, this agent would just be something like a deep network or a linear network that just immediately returns an action, right? It gets a state, immediately returns an action. It just executes the circuit, and that's all there is to it. Now what we want to do is think about the situation where this agent also has this world simulator in its head, kind of like you can simulate the future to some degree, not at high fidelity, but all of you can simulate the future, and you do that sometimes to make decisions. And when we get the state of the world, the agent can spend some time playing around with that simulator to decide what to do right now in the current state. Right? And the amount of time that you spend, you're hoping that you get algorithms that are anytime algorithms, in the sense that if you let the agent spend more and more time playing with a simulator in between decision steps, the decisions will be better and better, right? And so you're kind of familiar. You might be familiar with this if you think about chess engines, right? The more time you give a chess engine to make a decision at each step, the better it's going to play, right? And so that's how you want to think about this agent using the world simulator. Of course, one thing the agent could do is just use the world simulator to come up with a neural network policy, if that's what it wanted to do, and then use that to execute immediately. But we're going to now have the option of using more time per decision to hopefully do better using that simulator. All right. So any questions about this model? All right. So this is just showing you a whole bunch of domains that we've played with here at OSU that have simulators. Lots of things. You can look at these on your own, but there's lots of simulators out there for pretty much any part of engineering. Simulation is very critical. So let's so when we talk about Monte Carlo planning, we're going to talk about having a simulation-based representation of the MDP, right? So we're not going to be so far. When we started the class, if I asked you to solve the MDP, we gave you a matrix, right, of values, and that was it. Now we're in a situation where the state space is too large to provide that matrix of values for R and T. And so what we're going to think of is we're going to have R and T and I. We'll talk about I, but this is an initial state distribution. These are all going to be, you want to think of them as just programs that you can call, that have an API that you can call. And so let's, and basically our planning algorithms, the algorithms we develop, are going to be just wrappers around those different programs. And so let's look at what those programs are. So the first program or I guess function that you have an API to is going to be the reward function. And here we're just going to say this function, you pass it a state and an action, and it returns a reward. And for now, we're just, in this part of the class, we're going to assume that it could be a randomized reward function. It doesn't really change anything. It could be deterministic, but we'll assume it's stochastic. All right, so just think of R as an arbitrary program, piece of code that I give you, and there's an agreed upon interface where you pass it a state and an action, and I return you a number. That's the reward. Similarly, we're going to be given a program for t that you pass it a state and an action, and it returns an s prime, a new state that is distributed according to the transition dynamics of the environment. Right? So again, t is just an arbitrary program, could be written in C, could be a big messy simulator that's a million lines of code, but at the end of the day, we have an interface to it, and we can call it. And then finally, I is just an initial state function, which is going to be useful for sort of giving us an initial state for the problem that we're interested in. And this might be deterministic. If you're playing a game of Go, the initial state function will just return a blank board. But it may be a distribution of states as well, depending on your application. All right, and so just again, I want to stress, these can be, just think of these as arbitrary programs that you have an API to, and Monte Carlo planning is basically about trying to create algorithms that use these programs as interfaces to these programs, and calls them some number of times, maybe millions of times, thousands of times, and after doing that, it will return an action. Our algorithms will return an action for the current state, right? So that's how you want to think about these. So any questions about this? All right, so fairly straightforward. So it is worth at least pointing out the similarities and differences between what we think of as pure reinforcement learning and what we're going to call Monte Carlo planning. And I've kind of alluded to this already, but we can sort of reiterate. So in pure reinforcement learning, the agent starts with no knowledge, and it's kind of embedded in the world, right? It's embedded in the world, and it wanders around in the world trying to learn what to do. And this, by being embedded in the world, it's sort of stuck. It's stuck where it is, right? It can't just say, oh, I want to be over there and get there. If it wants to be over there, it's going to have to figure out how to get over there, right? So it's stuck in the world and can only get to places where its actions lead it. Monte Carlo planning, the agent begins with no declarative knowledge of the world. It doesn't know the rules in a declarative way, but it has this simulator in its head that it can actually say, hey, I want to know what would happen if I was over in that state and I took a particular action. It can just ask the simulator, right? A reinforcement learning agent can't do that. And so that's sort of the real power here. You think about it as the simulator gives if you want to think about the RL agent, it gives the RL agent an ability to teleport anywhere it wants and to try any action it wants. And so if you modify the RL formalism so that the agent can teleport to wherever it wants and take any action it wants and observe the effect, then you effectively end up in Monte Carlo planning. So it's really this teleportation ability that we get. And some terminology that you may see sometimes, I don't know, different people use different terminology, but I like to use the terminology of a strong simulator versus a weak simulator. So Monte Carlo planning is sometimes called RL, reinforcement learning with a strong simulator, where the strong simulator lets you go anywhere you want and take any action you want at any time, right? And whereas pure reinforcement learning is sometimes called RL with a weak simulator. And the only thing the weak simulator allows you to do sometimes is to reset to an initial state. Sometimes maybe not even that. But usually when we're doing episodic reinforcement learning, you're able to reset. Like if you go 1,000 steps and you think you should stop, you can reset and go to the next episode. And that's often how traditional reinforcement learning is formulated, right? So RL with a weak simulator versus strong simulator, and we can say that a strong simulator can always can do the job of a weak simulator, right? So you can you can at least do pure RL in the Monte Carlo planning framework, but not vice versa, right? If you only have a weak simulator, you can't necessarily do Monte Carlo planning. Um, and so there are cases where you'll come across simulators that were developed, over years and years, and it's really hard to turn them into strong simulators. And the reason is, these simulators have lots of legacy code, and there's lots of internal state in the program underlying the simulator that's hard to get your hands on to like reset to arbitrary places. So I've spent lots of time in the past, or students have spent lots of time trying to take, like for example, we had a real-time strategy game engine called Wargis, which was a clone of Warcraft, and we wanted to make a strong simulator out of it, and it was really hard to do because there were things internally that there were certain variables that you had to track down that if you didn't sort of reset them, that you wouldn't get the exact same performance. So sometimes this is not so easy to take a simulator and make it a strong simulator, but if you have influence when you're getting into an AI application and people are developing a simulator, you want to sort of make sure that all of the state of the simulator is very clear, and that then makes it really easy to make a strong simulator. All right. So any questions about this? All right. This is something I think is pretty important because it kind of elucidates how in some ways the protocol that we use for the vast majority of reinforcement learning that you see in the literature is just not really using the simulator to its full extent, right? We're just pretending we're in this weak simulator, but we really have strong simulators. And you could argue, well, but in the real world, reinforcement learning agents can't use, you don't have a strong simulator. I want them to learn in the real world, but nobody does that right now, right? You're always learning with a simulator, and so why not exploit it to its fullest? And that's what you could say, that Atari experiment that I showed you with imitation learning, that's what they were doing, right? They were saying, okay, we've got a strong simulator for Atari. We can do Monte Carlo planning to compute really good decisions, and then we can use learning to try to mimic those decisions. That was what I mean by exploiting a strong simulator versus DQN is treating the Atari simulator like it's a weak simulator. And it's sort of stuck in the world and can't teleport. All right. So we motivated Monte Carlo planning by saying we want to solve really large problems, but we're actually going to start off by talking about Monte Carlo planning for single state MDPs, which seems kind of strange at first, but the reason is. This corresponds to something called the multi-arm bandit problem. And this problem is interesting in its own right and has applications in its own right, so it's worth studying. It's almost the purest form of reinforcement learning that you could think of. So that's one reason to study it. It's just interesting in its own right and has applications. But also we're going to use these multi-arm bandit algorithms as building blocks for more elaborate Monte Carlo planning algorithms later on. So that's why we're going to start out with a single state case. All right. So let's talk about the multi-arm bandit problem. So we're gonna be in a situation which we have a single state of the MDP, right? And this seems kind of crazy, right? There's not a whole lot that you can do. And we're going to talk about a time horizon of 1. So we're going to have a single state, and you get to take a single action in the MDP, and then your episode's done. So it's basically the reason it's called a multi-arm bandit is this sort of this problem came about in the 60s. We'll talk a little bit about the origins, but they imagine it as you have, so a bandit is one of these slot machines that are in Las Vegas. People pull the lever and it gives a payout, right? And in real slot machines, if you pull the lever enough times, you're just going to lose money, right? If you pull the lever forever, you're going to lose money, right? Otherwise, Vegas would not make money. So, but here we imagine the slot machines, like some of them may make money and some may lose money on average, and some may break even on average. And you'd like to try to find the slot machine that's going to be best for you by actually pulling the levers. You get to pull them one by one, and sort of what is the best strategy for identifying the best machine. That's sort of one objective for multi-arm bandits. But that's the name of that's why we have the name of the problem. They sort of thought about bandits or slot machines in the beginning. So these types of problems arise in many situations, and the origins are actually about clinical trials. And just to make sure we have the analogy to the MDP, so here's our single state. The bandits each correspond to an action. Okay, so each action corresponds to one of the bandits or one of the arms, and when we pull an arm, it corresponds to basically getting a random sample of the reward. So here, it's important to remember we're thinking about stochastic reward functions. If I don't have stochastic reward functions, I have to make these pictures more complicated, so we're just going to have stochastic reward functions. And again, this could correspond to a piece of code that you have that does something to return a number, right? So that's how this relates to an MDP. But the origins really came about in clinical trials, and we'll talk about that example in a minute. And also, ad placement is a very common place where you see bandit algorithms being applied in industry. We haven't really talked about what the concrete objective is for a bandit problem, right? I can give you a bandit problem, which is just, here's a bunch of arms that you can pull. But what are you trying to achieve? And there are different objectives, different ways of formulating what your objective is. And we're going to look at three of them. One is going to be something like you're going to try to find a near optimal arm with high probability as quickly as you can. That's sort of or try to give guarantees on how many pulls you need to find a near optimal arm. That's going to be called the pack objective, and we'll study that probably first. The other objective is cumulative regret, which is basically you're going to try to maximize over the lifetime of arm pulls how much rewards you get, right? And so it seems like what you would want to do is you're going to be, in the beginning, you have no idea which arms give you more reward than others. And remember, these are random rewards. Every time you pull a slot machine's arm, it gives you a different payout. But over time, you want to find the machines that have the higher expected reward, and you want to pull them more. Right? That's what you would do. And then finally, we have a simple regret objective, which really is about identifying an arm with a highest reward very quickly. And there are some differences between the pack and simple regret objective that we'll get into. But those are the three objectives that we're going to talk about, and there are slightly different algorithms for dealing with them. And a bandit algorithm is nothing more than an algorithm that says, okay, here's a list of all the arms I've pulled in the past and all the payoffs I got from those pulls. What arm should I pull next? That's what the bandit algorithm has to tell you. So it gets the history of what you've done, and then it returns an arm to pull, right? And an algorithm, what arm to pull depends on what objective you're trying to optimize. Right, so any questions about this? All right, so let's look at some concrete. Wow, this is just general stuff. Bandit algorithms show up everywhere, but here's a concrete example of clinical trials where, and this is really in the 60s, where it grew out of statistics, this bandit problem, and really it's sort of a form of adaptive experimental design. So a clinical trial, the typical thing that you would want to do is you've got, maybe there's two different treatments and a placebo, and you want to know which one is best, right? Or if there's a significant difference. And often what's done in practice is you say, well, this is how many participants I need for the different treatments. You'll randomize, and you'll run the trial with equal numbers of participants per treatment, which seems kind of it's kind of a shame to do that, for things like cancer treatments, when some people are going to be in the placebo side of things. That's kind of unfortunate, right? Because they have no chance of getting the benefits of these potentially good drugs. And so bandit algorithms, the origins actually came out of thinking about trying to do these trials adaptively, which are very hard to do and to get statistical guarantees, and very controversial in some ways from a statistical point of view. But you'd like to, if you find that one treatment is actually doing pretty well, maybe you'd like to move more people to that treatment and have fewer people on the placebo, right? To sort of get a bigger benefit that you're actually seeing during the trial, rather than having equal populations in all of the treatments. And so that's one of the ways that bandit problems were originally thought about. And here, we can think about the arms, or the actions, are the possible treatments. The arm poles are applying a treatment to an individual, and the rewards are the outcome of the treatment. And there are lots of ways of measuring medical outcomes. And the objective, or one of the objectives that you could have, is you want to sort of maximize the benefit for the total population on the trial, right? And the ideal world, how things would work is there's always trials going on, and it's just most all the people are on the best treatment right now, and a few of them are on experimental treatments. So this is basically what you get with clinical trials. So as I said, this is a very we'll finish this next time. I think we'll go over, because I'll take at least 5 minutes for this, because I like to rant about advertising, or my distaste for advertising. So we'll meet on Friday, and we'll talk more about this.